Hello, welcome to this video. Myself Vinayak Kondungar, working as an assistant professor in the Department of Electronics and Communication Engineering, SG Balachandra Institute of Technology, Belagavi. In this particular video, we will be discussing what do you mean by subsystem design and layout. So for the outline or the topics that will be covered under this subsystem design and layout are: first one, the architectural issues; second, the switch logic; then third is the gate restoration logic. So going on to the first point, that is architectural issues. Now what do you mean by an architectural issues? As you know that whenever you're designing any architecture, you will be coming across a lot many types of problems. The first problem that you will be encountering in this architectural issue is how to deep uh, divide your large complex system into a simple system, that is, we call it as a subsystem. Now this subsystem, if it is a basic building element of your design, then that element we call it as a leaf cell. So this is nothing but that what you actually mean by a leaf cell. Then the next turn is how you actually go into the structural design, that is how you are going to regularly use a leaf cell. That is, in case of a regularity, that is, once you develop the leaf cell, the same leaf cell can be used repeatedly again and again in your subsystem. That is, you are not going to develop the leaf cell again and again. The time that is required to develop one leaf cell is not going to be used for successive leaf cell generation or the development of your successive element. That is, a single leaf cell is being repeatedly used. That is, we call it as high regularity. Then the second point is how you are going to interconnect these leaf cells in the system. That is, we come across the placement and routing. Then the third point in the architectural issue is how you are going to approach or what the methods you are going to follow for the logical and systematic approach to the VLSI. So which type of method you are going to follow. These are the few architectural issues that you are actually coming across. Then the first point that you are actually going into an architectural issue, that is when you are actually designing a processor, or you can say in any design process, a logical and systematic approach is essential. What are those essential points? The first thing is you need to define the requirement. That is, without any the problem statement, you are not going to able to start your thinking. So you are actually thinking, what is my actual requirement? That is, you need to properly and carefully define what are the requirements to achieve your subsystem design. Then the second point is how you are going to partition your overall architecture into appropriate subsystems. That is, a problem is given, that is architecture, how you are going to divide that architecture so that it will be easy for you to concentrate on a particular part of your architecture. Some simultaneously other people will also be involved in the designing of their part of the section, and once all the architecture is over, you need to club it into a single architecture. So here partitioning of the architecture becomes an important parameter. The third point is how you are going to connect those elements. The elements in the sense the architecture, that is which communication path you are going to use, that is with respect to the routings, how you are actually routing, what type of routing you are going to use, what happens if I use any particular type of routing, what will be its effect on that, so on so forth. Then next is the floor plan, that is how you are going to place your elements, that is in which direction, in which form you are going to place your logic elements, because placement makes an important parameter, because ultimately the area used for your architecture should be as small as possible. If it is crossing, then it may be having the other effects, like it may be consuming large amount of power, heat dissipation may be more, efficiency may be less. So with respect to this, we need to be very careful how you are actually placing your logic elements. Then next comes is for your regular structures. This, what do you mean by regular structure? Regular structure is nothing but if you are having an architecture wherein in a part of the element should be repeatedly used in your successive architecture. That means what? Successive architecture in the sense you are not going to make the design, or you are not going to invest the design time again and again for the same parameter. To understand this, you can take the simple example of addition of 6 subjects for 50 or x number of students, wherein you are going to find the number of percentage of each student, or the highest mark score for each student. So you are basically performing the addition operation, or you can say the arithmetic operation. So you are not going to design this ALU for every person. So you are going to take it in the form of a loop, and you are going to perform that particular action. So here you are actually taking a repetition of that particular, or you can say the operation. That is, you are basically using here a loop operation. In the loop operation, you are adding the subjects of so and so, that is 6 subjects or 8 subjects, and you are getting the output. So here we are basically aiming for regularity in the structure. Then the next one is how you are going to draw it, that is the strict or the symbolic diagram. So in the strict or in the symbolic diagram, you know that you are going to basically use the different types of color palettes. These color palettes are indicating the different color codes, or you can say the layers of your metals or MOS layers. So once you draw the strict diagram or the symbolic diagram, you will come to know what are the errors that you may come across. So in this particular part also you will be doing some rectification work. Once this is correct, then you can go for the next step, that is you need to convert each cell into a layer. That is, now you need to club all your leaf cells with the routings, and you have to perform the placement, that we call it as a layout. Then the last point, that is carry out the design rule check on each cell, which is an very important. Unless and until you are having the thorough output or the verification is done on each cell, it is not feasible for you to move into the next step. So it is mandatory that you check with all the perspective, that is parameters related to that particular logic element. Unless and until there is a satisfaction, you please do not move for the next step of your design cycle. Then once you do it, simulate the entire system performance. That is, check with all the perspective of your entire module. Then moving on to the next one is, what do you mean by a simple switch logic? Switch logic are basically used for your on the pass transistor or transmission gate. Now first one you can see here is a simple diagram. These are some logic arrangements. In this particular logic arrangement, you can see that I have taken 4 basic NMOS structures. Each of these 4 NMOS structures, that is A, B, C and D, are connected in a series. One terminal of your NMOS A is connected to V in, the other terminal of the A is connected to B, so on and so forth, and the last terminal, that is your D, wherein you are seeing the output V out. That means I'll be applying the voltage at this particular point of the terminal of MOSFET A, and I'm going to take the output from MOSFET D. Now when I give the gate voltages for A, B, C and D as 1, then whatever my input value is present, the same value will be the output. Provided A, B, C, D have to be 1. If any of the gate is having 0, that means that particular NMOS will be off. To understand this, let us take an example here. Now let us assume that A is equal to 1, B is equal to 2, C is, sorry, A is 1, B is 1, C is 0, D is 1. In this particular case, if I give the voltage as A for 1, B for 1, C is 0, D is 0 and input is 1. In this case, NMOS related to C is in the off condition. That means the output here will be 0 because the circuit is closed here. But if you make this change, slight change, now if I apply voltage 1 to C, that means the output voltage will be 1 because now all the MOSFETs are in the off state. If suppose the voltage Vin is 0, then the output will also be 0 naturally. Okay, so this is a simple switch wherein it is just working like an on-off switch. Now going for the next example. Here one more example I have taken, that is with respect to a simple 4 MOSFETs along with the inverter. Okay. Now in this particular case, you can just check here. Here A, B, C, D is connected to Vin, E, F, G, H are connected to the inputs of your, the output of your inverter 1, then connected to the output of input of the inverter 2, and the output is obtained here. Now in this case, your output is 1 only when A, B, C, D, then E, F, G, H, okay, are 1. Along with that, the output of the first inverter should also be high. Then only you will be getting the output as 1. But if A, B, C, D, E, F, G, H and output of the inverter, if it is other than 1, then the output will not be 1. You will not be able to predict what the output is. Why? Because if one of the switch in EFGH is off, then even though you are getting the output till that particular terminal, you will not be getting the output at the final. So it is unpredictable. That is, V out is not known unless and until A, B, C, D, E, F, G, H are all high, and irrespective of whether the input is 0 or 1, this output will be obtained. But if any of the gates of A, B, C, D, E, F, G, H are not 1, then it is difficult for you to predict what is the output. This is one more example. Now let us go into the one more example of a pass transistor. Now here we are using a NMOS 3 input OR gate. In this particular case, wherein you can see that 3 gates are in series and 3 are its negation part. That is what we call it is, if A is equal to 0, then A bar will be 1. That is complement part. One is in series, then other one is in parallel combination. Then the structure of this is connected to your V out. Now here V out is equal to what, as per the equation, is A plus B plus C. Here and Vout bar will be A bar dot B bar dot C bar. Now in this particular case, let us assume that A is 1, B is 1, C is 1. That means here you are getting all the, what you can say, these particular transistors, that is NMOS transistors, are 1, and whatever VDD you are applying, you will be getting at Vout. Now assume that A bar, B bar, C bar are 0. That means all are on, that is whether in series connection or in parallel connection, all are in the on state. Now in the on state, what happens, your output will be equal to VDD, but some part will be degraded. Now if A bar, B bar, C bar are 1, that means the series part is in off state and output will be VDD. So this is one type of example wherein you are actually passing in the switch in the on and off condition. Similarly, you can go for a pass transistor, that is a transmission gate. Now this is a 5-way selector, and for a transmission gate, you know that you are having uh, that is A bar and A and input and output. In this particular case, the output is nothing but V1 into A, V2 plus V2 into B plus V3 into C plus V4 into D plus V5 into E, assuming that A, B, C, D and E are mutually exclusive. That is, here in the 5-way selector, whichever particular uh, terminal, that is either A, B, C, D or E, is 1, that particular switch will be on. Suppose let us assume that C is equal to 1. That means only C switch will be on. So this is any one of the switch can be on in this particular case. So it is called as a 5-way selector. With this, we will be moving on to the next example, that is pass transistor and transmission gate. Now in the case of a pass transmission or a transmission gate, in this case the switch and the switch logic must be formed by simple N or P transistor. As you know that without the usage of the N MOSFET or a P MOSFET, it is difficult for you to design a simple switch. Then a second point is signal degradation occurs in pass transistor logic. As you know that there will be some voltage degraded in your output, and this is due to the pulling down of that particular signal. So here when you apply 5 volts at the input, you are not going to get 5 volts at the output. Some part of your voltage, let us assume that 0.7 voltage of that particular whatever you applied will be used by the MOSFET to go into the conduction mode, because zero point 0.7 is your required voltage for the MOSFET to make itself activate. That is, in this particular 0.7 voltage, your channel is actually formed. Once the channel is formed, there is a movement of your carriers, that is electric current is going to pass through that particular logic, that is your MOSFET. So at the output, you are not going to get the exact 5 volts, but you will be getting lesser than the 5 volts. So signal degradation occurs in transistor logic. But in case of a transmission gate, there is no signal degradation. But when you compare with the pass transistor logic and the transmission gate, obviously transmission gate is going to require more area. Why? Because in case of a transmission gate, it is a combination of a NMOS and a PMOS connected in parallel. Whereas in the pass transistor, either you will be using a NMOS or you will be using a PMOS. So here your in the transmission gate, the area required will be naturally more when compared to your pass transistor. So let us see this operation. Now here in the first figure you can see there a simple pass transistor switch, and in the second case you can see a simple transmission gate. Or by just now by looking at the figure itself, it is very easy for you to say which is going to use more area. In the first case, that is in the case of a transistor logic, since it is only one, the area is required is less. But in case of a transmission gate, as you can see, it is a combination, or you can say parallel connection of your P and a N device. So naturally you are going to use a large area. Then moving on to some more examples, what you are going to mean by degradation. Now it will be still more clearer in this particular case. Now let us go into the first figure. Now this is your first figure. Okay. Now you can see this is a NMOS switch. Okay. In the NMOS switch, when I apply voltage 0, okay, naturally in the case of a NMOS, the input is 0. Now it going to depend on what is your voltage at the gate terminal. So now assume that the gate terminal you are having the voltage 5. That means when you apply voltage 5, the gate, or you can say, is going to make your NMOS device on. Now in the case when the device is on, what is the input here? 0. So this 0 voltage will occur at the output side. So that means there won't be any degradation for the switch. Now when I apply input voltage 5, check here, the output is not actually 5 volts. It is less than 5 volts. So here you can say the output is degraded. That is, this is occurring for logic 1. That is 5 volts is nothing but it is logic 1. So here the output is degraded by logic 1. That is, some part of your energy is utilized for the operation of your MOSFETs. Now if you go for the other case, that is for a PMOS. Now if you go for the next part, that is in case of a PMOS, which is the vice versa of your NMOS. In the case, assume that you are applying 0 volts. 0 means, that means PMOS will be in the on state. Now when I apply 0 volts, now since this device is on, it is not going to give whatever the input is. Now we have assumed that it is a 0 here. So here in this case you will be having degraded logic 0. Why? Because you are not going to get the exact 0 volts. You will be getting 1 volt. But when you apply 5 volts at the input, output will be 5 volts. So you can just observe that whatever the operation you can see in a NMOS, its vice versa will be observed in a PMOS switch. Now with this same or the concept, we can check for a transmission gate. In the transmission gate, as you have studied in the previous slide, that there won't be any signal degradation. How is it possible? Now you can see that individually when you operate it, there will be either degradation of a logic 1 or there will be a degradation of logic 0. But when you make the combination, naturally there will be a compensation for each other. That is, mutually they will be compensating each other. That is PMOS and the NMOS. And you know that in a transmission gate, it is a combination of a PMOS and a NMOS. So in case of a NMOS, there is a logic degradation 1, which will be compensated by your PMOS, and degradation of logic 0 that is occurring in PMOS is compensated by the NMOS. So there won't be any degradation in the case of a transmission gate. So we always say that whenever you want to use a switch, it is better to use a transmission gate, since there is no degradation, or simply you can say there is no signal degradation taking place. So this is nothing but a transmission gate wherein you are applying 0, you are getting output 0. If you are applying high voltage, that is 5 volts, you are going to get 5 volts. That means in this case there is no signal degradation. The symbol for a transmission gate is as shown in this particular part. Now if you combine two NMOS like what you can see in the third part. Now here you can see the gate terminal of this particular NMOS is connected to the output of this particular NMOS. So that here you can see logic 1 are applied at both inputs of your NMOS. But here the output at this end will not be what you are going to get. It's because since it is a NMOS, there will be degradation of logic 1, and that degradation is carried over to the gate terminal of your next MOSFET. So that tells you that whatever the signal degradation has occurred, now you need to check what is its voltage, whether that voltage is sufficient enough to make this particular MOSFET on, or is it insufficient. If it is sufficient, then the output at this part will not be what you are having it. You would be having some degradation, and its equation is given by VDD minus 2 times VTP. That is, one TP is from this, another TP is from this. That is signal degradation. So 2 VTP. So the final output will be VDD minus VTP. So moving on to the next part, with this particular switch logic, let us move into the next part, that is gate restoration logic. What do you mean by gate restoration logic? Now gate logic is actually based on a simple arrangement. Usually we use the simplest arrangement is the inverter. Now see here, the first figure shows a simple arrangement of a inverter, but this arrangement is in the NMOS technology. Now in case of a NMOS technology, you know that you will be using enhancement mode transistor. So here you are not going to use a PMOS. So in this particular slide, you can see that you are basically going to study about the gate restoration logic. Now in the first figure, wherein you are going to use the NMOS technology, and in the second figure, you are going to use the CMOS technology. Now what is the difference between this? Basically here you need to take the ratio of a pull up and pull down transistors, that is ZPU, and divided by ZPD. That is, this upper part is a pull up and bottom part is a pull down transistor. Now here you can see that basically I am going to take the layout for your MOSFET, that is your inverter. Now in this case we are actually interested in to check what the ratios of your pull up and pull down transistors occur. Now in the first figure you can see that now in this particular example you can see that the length of your PMOS, since it is a NMOS technology, so the NMOS here the length is a 16 lambda, and in this case it is a 2 lambda. Width for your poly is a 2 lambda. So let us discuss how the ratio is going to be calculated. Now the ratio that is for your pull up transistor. So here you can see ZPU is nothing but length divided by the width. Now the length is what? 16 lambda. Width is 2 lambda. So 16 divided by 2 will give you 8. The resistance with respect to the pull up is what? Impedance, that is a pull up impedance into the sheet resistance. So if you assume that the sheet resistance is 10 kilo ohm, that means ZPU is 8 into 10 is 80 kilo ohm. Similarly, we are going to go for the pull down transistor. In the case of a pull down transistor, it will be 10 kilo ohm. Then the other important parameter that you need to calculate in this particular part is the power dissipation. Just by going through this particular equation, you will see that the power dissipated in this particular structure, or whatever the specification you have taken, is a 0.28 millivolts, considering that the input capacitance is 1 Cg. Now the main part what you are actually going to understand here is, if the ratios are different, okay, that means naturally the power dissipations will be different. But our motive is to design the circuit is what, you need to use the ratios judiciously or technically correct ratio, so that the power dissipation of that particular circuit will be as less as possible. Why it has to be as less as possible? Because once you develop the entire architecture, successive, that is whatever small heat that is being liberated by individual elements will get added on, and once the complete architecture is checked, the power dissipated by the entire architecture will be very large. So these small individual heat dissipations of your circuits should be as less as possible. This is for the first case. Now one more case what you can check here is wherein I have taken a different ratio. That is, in the second case I have taken 8 lambda. In the previous case I had taken 16 lambda and 2 lambda. In this case I am taking 8 lambda and 4 lambda. In this case what happens is, power dissipation, you can just check here, it is 0.56 millivolt. Actually the voltage here has increased, because I have considered here as the voltage to be same resistance of your NMOS to be 10 kilo ohm. Okay, now you can see that here in this particular case the voltage, or you can the power dissipation is slightly increased, wherein when you have chosen a different what you can say length and width. So this becomes an important parameter. So it is very essential for you to decide what the ratios have to be selected, because different approaches will have different power dissipation, and the area occupied by the inverter will also be different. So the CMOS inverter carries no static current, and hence there won't be no power dissipation unless and until the inverter performs in the switching mode. So here the CMOS circuit should have no dissipation problem, but it is difficult for you to develop a CMOS circuit without any power dissipation. There will be some slight percent of your power dissipation. No circuit is going to have zero power dissipation. So this is the example with respect to the gate. Moving on to the, yes, now you can see here that the two NAND gate, the circuit, basically the area what you are going to study is, see, in the particular case of a pull-up side, here we are using only one MOSFET, whereas in case of a CMOS we are using two MOSFETs, that is a PMOS devices are used here. So naturally the area taken for the pull-up side is very large. So you need to compensate between the pull up as well as the pull down side, because this is going to have the effects on your output. So this is the first parameter, and the second parameter is with respect to your delay. Now see here, as I have already explained here, the inputs what you are going to add should have adjustment with respect to your pull up transistor channel, so that you can maintain the required overall ratio. And the second parameter is with respect to the gate delay. The For an N input, the length and the resistance of the pull-up transistor must be increased by a factor of N to keep the correct ratio, and the delay associated with this NMOS NAND is given by this particular equation. T NAND is equal to N times T. So whatever is the delay for one particular time, you need to multiply that with n number of MOSFETs. So it is basically T NAND is equal to N times T. So these are the two significant factors of your NAND gate. So similarly, these two significant factors, that is your gate area and gate delay, will hold good for a next part. That is when you are going to study your NOR gate. Now in the case of a NOR gate, the basic change in this particular NOR gate is in the bottom part. Now you can see here, in the previous case it was in the series connection, now it is in the parallel connection. So there will be some change in the effect. So here in the case of a NOR gate, the significant factors what is both the transistors of a NMOS in the case of a NOR gate provide a path to the ground for pull-up transistors. Therefore, the ratios must be such that any one conducting pull-down transistor will give the appropriate inverter-like transfer characteristics. So it is not mandatory for all the MOSFETs to be on in the case of a NMOS in the case of NOR gate, because since both are connected in parallel, any one of the MOSFET, if it is on, it is naturally going to pull your output towards the ground. That is, it starts pulling your voltage that is applied at the output. So with this video, I have basically discussed about what are the architectural issues, what do you mean by switch logic, and what are the parameters related to your gate restoration logic. Thank you.